All right, in this video, I'm going to be looking at section 5.6, the section on exponents and scientific notation. All right, so first off, you probably already know that if you have an expression like 2 raised to the third power, 2 to the third, that means 2 times 2 times 2. Okay? The 2 is considered the base, is called the base of the expression. And the 3 is the exponent. Sometimes we say power, okay? Exponent or power. And then the whole thing is called an exponential expression. All right, so when the exponent is positive, we know a whole lot about it. So if this exponent n is a positive integer, we know what it's telling us is to take the base, which in this case is a, and multiply it by itself n times. So the exponent tells you how many times to multiply the base by itself. So a is the base, and n is the exponent. All right, now not paying attention to what the base is a big issue when simplifying exponential expressions. So you need to watch the watch the base, or think about what's the base. Okay? All right, so let's take a look at these problems down here. Move that over just a little. Okay, so on the first one, first and second one are probably the most important. So on the first one, the exponent is really only being applied to the 5. This first one is really taking 5 and squaring it. The base is really 5, and then finding its opposite. Okay? So that first one, let me write it a little differently. So that first one, it's like that negative needs to be pulled away a little bit from the rest of the expression. It's like the opposite of 5 squared. So it's like -1 times 5 times 5. So that one's going to be -25. Where if it's in parentheses and squared, you're going to multiply -5 times itself and get a positive 25. Of course, 5 squared, the base would be 5. So you get 25. Okay. Now, on these last two, I want you to notice how on this one, the 3 is only really being applied to the x, where on the last one, it's being applied to 2x. So this one means 2 times x times x times x, and the best way to write that is 2x to the third. But the last one really means 2x times 2x times 2x. So that's going to turn out to really be, there's really 3 2's multiplied together and 3 x's, so that's going to wind up being 8x to the third. Very different. All right, now what I want to do down here, we know a lot about exponents that are positive, but I want to help you see what an exponent of 0 or what a negative integer exponent might mean. So I just want to look at some patterns to figure that out. So if I did 3 raised to the 4th power, we know that means 3 times itself 4 times. 3 times 3 is 9, so we have 9 times 9, that would be 81. We know 3 to the third would be 3 3's multiplied together, so that's going to be 27. What I'm doing in this pattern is I'm keeping the base 3, but I'm making the exponent, I'm subtracting 1 from the previous exponent. So now I have 3 to the second. So I only have 2 3's, and that would be 9. Let me do one more. 3 to the first would be 1 3. So when my exponents, when I subtract it, so we're focusing on how I had a 4, that I subtract 1, got a 3, got a 2, got a 1. That when the exponent goes down by 1, what's happening over here is I'm losing one of these 3's, aren't I? So when the exponent goes down by 1, it's like one of these 3's goes away. Well, that's because when the exponent goes down by 1, it's really, I could have taken 81 and divided by 3 to make the 27 happen. Okay, when I drop a 1 on the exponent, that means I'm going to lose one of the 3's. So 27 divided by 3 would have given me the 9. So when I go drop 1 on the exponent, I could divide by 3 to see what my answer is. And notice we're getting what we're expecting. Now I'm doing this because I'm going to continue that pattern. So I'm going to still have a base of 3, but I'm going to drop the exponent by 1, which means I'll have an exponent of 0 there. So we're trying to figure out what that would be. And what I noticed is every time I dropped the exponent by 1, I could have thought about dividing by 3. Well, 3 divided by 3 would equal 1. So that tells us that we want 3 raised to the 0 power to wind up equaling 1. So it gives us a definition for what we want the 0 exponent to be. Okay? And then notice if I keep that base of 3, but I subtract 1 from the exponent, I would now have a negative exponent. Okay? So I could continue this idea, and I could divide 1 by 3, right? And when I divide 1 by 3, don't I get a 1/3? Okay, then I could take and do that as many times as I wanted. I'm only going to do it one more. And when I do that one, I would have to take 1/3 divided by 3, which is 1/3 times 1/3, which is 1/9. Okay. Actually, I'll squeeze in one more. And 3 to the negative 3, divide by 3 here. Let me make that green like the others were. Oops. Okay, so when I drop that exponent one more time, and I think about dividing what I had by 3, that one turns out to be 1/27th. Okay. All right, and then notice that 3 to the first was 3. Notice that that negative on the exponent made it 3 to the negative 1, 1/3. And then look at how 3 to the second is 9, 3 to the negative second is 1/9. 3 to the third, 27, 3 to the negative third, 1/27. All right, so what we did that for is because math is all about patterns. Patterns, we need nice, consistent patterns. So we want to define things so that our patterns remain consistent. So what this is telling us is that when we have a number raised to a 0 power, we need that to equal 1. And when we have a number raised to a negative exponent, we need that to equal 1/, like a reciprocal. Okay? So it's 1/3 to the first. All right, so note that a negative exponent, so if you have a negative exponent, you don't get, doesn't give you a negative number for an answer. You get 1/, something. You get a reciprocal. So a negative exponent doesn't make the number negative. What you really get is 1/, something. Okay? All right, now do want to consider one issue though. 0 is a little weird because if we had 0 to the third, that would be 0 times 0 times 0. We know that's 0. 0 to the second, 0 times 0, okay? Also 0. 0 to the first would be 0. So if we had 0 to the 0, wouldn't we need that in order for that pattern to be consistent? We would need that to be 0, okay? All right. 0 to the 0 seems like it needs to be 0. But if I do this, 3 is the base with 0 as the exponent, then that's equal to 1 for the reason we found right here. And then if I made it a base of 2 raised to the 0 power, then that would be 1. 1 raised to the 0 power would be 1. And then I would want 0 to the 0 power to be 1. But I can't have an expression. I can't have this equal to two different things. But see, for these patterns to be consistent, I would need it to be a 0 some of the time, a 1 some of the time. So 0 raised to the 0 power doesn't have an answer. We say that it is indeterminate. That just means you can't determine the answer to that. Okay, so any number raised to the 0 power equals 1, except for when the base is 0. All right, so let's look on the next page. On the next page, I've got the, we're going to summarize the rules. For if your exponents are positive, if the n, not positive, but if the exponents, if the n and the m that are used here are positive integers, so that means 1, 2, 3 on up, and then the base can be any real number, just not 0, then a to the 0 power would equal 1. Okay. So this case where 0 equal to the 0 power, that is indeterminate. But any other thing raised to the 0 power equals 1. Now here we have the negative on it. So now we're thinking about what happened when we had, okay, when we had something like that. Something raised to a negative exponent isn't a negative number. The negative exponent means 1 over. It means to take the reciprocal. So you'd have 1 over a to the nth power. Let me move that down a little bit and get rid of the circle so I can write that. That means 1 over a raised to the nth power. And then this one happens quite a bit. So I just wanted you to know that on this one, we know a to the negative m means 1 over a to the m. And then b to the negative m, n means 1 over b to the n. It actually can be moved up to the top. So let me show you that, like why we can do that. Okay. So this means 1 over a to the m. This one means 1 over b to the n, and that's really division. So let me rewrite it as a regular division. And then when you're dividing fractions, you keep, change, flip, and that b to the n winds up on top with the a raised to the m on the bottom. Okay, so that's the justification for that. All right, now we're going to look at just a couple of strings of expressions where you'll notice that it's important to pay attention to the base. What's the base in each of these cases? Okay, so let me move this guy over a little bit. Just a little space there, a little space here. Okay, all right. So on question number 2, you should think about these first, and then you can just check them. Okay. So 4 squared, that's just 4 times 4, so we know that's 16. Now these two are that situation where you have both taken the opposite and squaring. But on the second one, you're really going to take the opposite after you've squared. That one really means -1 times 4 times 4, so you get a -16. Where the third one really means -4 times itself, and you get a +16. All right, on the fourth one, you got to be careful because a lot of times when you see minus and negative, you think, oh, I can just make that positive. But the issue is that this minus right here is like -1 times that -4 squared. So multiplication happens after the squaring happens. So you would do the -4 times -4 and then come back and multiply by the -1. So you're going to get 16 for that square of -4, and then you're going to take its opposite. Now the last three, the exponent is negative. So you're going to be expecting these to turn out to be fractions. Remember, a negative exponent doesn't mean a negative number. That would mean 1 over 4 to the second, and then 1 over 4 to the second would be 1 over 16. On the second one, this negative is not stuck on the 4. They didn't put it in parentheses. You should think about it as -1 times 4 to the -2nd power. So that's -1 times 1 over 4 squared. So that's 1 over 16, but then you have to take its opposite. Okay. Right, and on the last one, the -4 is in parentheses. So this one means 1 over -4 still in parentheses, but now to the 2nd power. Then that's going to wind up being 1 over positive 16. Think about the base. Ask yourself, what's the base? Before you do it. In other words, what's the exponent really getting applied to? All right, now question number 3, when something's raised to the 0 power, we found out that's defined to equal a 1. So you might think all of these are going to turn out to be 1, but it's not the case. Okay, so here, first one, 5 is raised to the 0 power. That one is 1. But on the second one, you would raise to the 0 power first. This is really -1 times 5 to the 0. You do exponents first and then take the opposite. But on the third one, the -5 is in parentheses, so the base is -5. And if you have a number raised to the 0 power, you get 1. Okay. Now on this next one, the 0 is only being applied to the -5. This means take the opposite. So it might help if you really just pull that negative away a little bit more. So -5 raised to the 0 power is 1, but then you'll need to multiply that by -1 to get your final answer. Okay. Now the last 3 have variables in them. So when you're looking at that, on this one, the base is just the x. On this one, the base is just the x. So the exponent is being applied just to x on those two. But on the last one, the base is -5x. By the way, we're assuming that x itself is not equal to 0. I didn't say that, but I should have. Okay, so on the last one, if we have something raised to the 0 power, that's going to be 1. And then on these other two, this is 5 times 1. Like x to the 0 would be 1, and then you multiply by 5. Okay? On -5x raised to the 0 power with no parenthesis, x to the 0 would be 1, and then you're going to multiply by -5. Okay?